In this video, we're going to talk about sound. So this diagram over here shows a string that's vibrating, and as it vibrates, it presses on air molecules, and as it vibrates in this direction, it compresses the air molecules together, called compressions, and as the string goes back in this direction, then the air fills in behind it and has less pressure, and that's called a rarefaction. So as the string vibrates, what happens is you get these compressions and rarefactions in the air, and that is the longitudinal wave that we interpret as sound. So down here, we've got a sine wave, and this is a graph, sometimes shown as a graph of the sound wave, although the sound wave itself is a longitudinal wave. This is a graph of pressure versus time, and it represents the sound wave. So the amplitude of the wave is interpreted as the loudness of the sound. So the bigger the compressions and rarefactions, the greater, the louder the sound is. And the frequency of the wave is interpreted by us as the pitch of the sound. And here's another diagram over here that shows a tuning fork, and the tuning fork prongs here are vibrating with simple harmonic motion, by the way, and is generating the same kinds of compressions and rarefactions that we've seen in the previous slide. Now, the distance between the compressions here is shown as the wavelength, and of course the waves, sound waves, have a velocity v. So they obey the same equation that we talked about for waves. Velocity is equal to frequency times wavelength. Now the velocity of sound varies with the medium, and there's a table in your book of different kinds of media and the speed of sound, and also the temperature. And in air, we can quickly calculate the velocity of air as 331 meters per second plus 0.6 T, where T is the Celsius temperature. By the way, there is a different equation in your textbook that's equivalent to this, but this is much easier to use. Okay, so here is an example. We want to calculate the wavelength of a 200 hertz sound wave in air if the temperature is 20 degrees. So from the 20 degrees, we are able to calculate the velocity of the sound wave. So that would be 331 plus 0.6 times 20, or 343. And so now we can use this equation and solve for lambda, the wavelength. So that equals the velocity divided by the frequency. 343 divided by the 200 hertz equals 1.7 meters. All right, now we're going to talk about intensity and intensity level of sounds. So we saw before intensity, we defined that as power per unit area. And now we're going to define something related, and it's called the intensity level of the sound. Now the intensity level, you've probably heard of these units before, it's called decibels, and this is defined as the logarithmic ratio of the intensity of the particular sound to the intensity of the threshold of hearing. And there's the equation. It's 10 times the log of base 10 is the intensity of the sound, and that is the threshold of hearing. The value of the threshold of hearing is 1 times 10 to the negative 12 watts per square meter. Okay, so let's try, this is a pretty simple example. We want to calculate the intensity level for the threshold of pain, which is 1 watt per square meter. So this is a sound so loud that it's causes pain to your eardrums, I guess. And so we use this formula up here. So it's 10 times log of 1 over 10 to the negative 12. So 1 divided by 10 to the negative 12 is 10 to the 12th power. When you take the log of that, it's just the value of the exponent. So that's 12. 12 times 10 is 120 decibels. Okay, here is another example that goes the opposite way. We've got a busy street, and it's got an intensity level of 75 decibels. We want to compute the intensity of the sound there. So 75 is equal to 10 log I over 10 to the negative 12. We're solving for this I. We can start off by dividing both sides by 10. So that gives us 7.5 is equal to the log of I over 10 to the negative 12. Now we have to take the inverse log of both sides of the equation. So when we do that, that puts this 7.5 up into a power of 10. So it's 10 to the 7.5 power equals, and on this side, we just lose the log. So it's I divided by 10 to the negative 12. So we solve for I. So that's 10 to the negative 12 times 10 to the 7.5 power. And that is 3.16 times 10 to the negative 5th watts per square meter. By the way, you can evaluate this on your calculator, usually by doing an inverse log, depending upon what kind of calculator you have. All right, here's one more problem, pretty simple one. If one sound has twice the intensity as the other, show that it has an intensity level of 3 dBs higher. Okay, so we're going to use the same equation here. The only difference is this is not going to be the threshold of hearing. These two ratios are just going to be the two sounds. And so that ratio is going to be 2, since this one has got twice the intensity of that one. So it just boils down to 10 log 2. So you determine the log of 2 on your calculator, which is 0.301 times 10, which is 3 decibels. Okay, now we're going to take a look at the Doppler effect. And the Doppler effect is the shift in frequency experienced when an observer, or by an observer, when the source and or the observer move relative to each other. So in this case, we're going to show an example of a moving source, which is the car, and two stationary observers here, X and Y. And the car, let's say, is blowing its horn as it passes observer Y. So as it goes in this direction, because it's emitting the sound and has a velocity of its own, what happens is the sound waves tend to get compressed in front of the vehicle, and behind it, it gets elongated. So as a result, observer Y here sees a shorter wavelength and a higher frequency, and observer X sees a longer wavelength and a lower frequency than what is actually emitted. Now the dramatic effect comes when Y here, when the car passes Y, because Y then experiences this change in frequency from high to low as the car passes. And perhaps you have had this experience where you're standing alongside of the road, especially if it's like the thruway, and cars are passing you. You can actually hear it from the road noise, from the tires, but it's more dramatic if the car happens to be leaning on its horn when it passes you. And I'm going to try to find a link that you can play that will show this change in frequency. And I'm sure you've all heard this. Okay, so here's an equation that allows you to actually compute the frequency of the observer, or the frequency perceived by the observer, when you know the frequency of the source. This is the velocity of the wave, so it's the velocity of sound, and this is the velocity of the source. Now you'll notice here it's plus equal, so this equation can be used for either when the source is approaching the observer, as in y here, or if the source is moving away from the observer, as in x. And it shows right here how the plus sign is used when the source is moving away from the observer, and the minus sign when it's moving toward the observer. Okay, here's the last situation that we were talking about in the previous slide, where the observer is in motion and the source is at rest. So we have individual Y here who is running toward the car. The car is, let's say, leaning on his horn, and she's in motion toward the car, and so therefore she encounters a greater number of wavelengths than is actually per unit time than is actually emitted, and so therefore that translates to a higher frequency. Now observer X here, who was moving away from the car, has just the opposite experience. He experiences or perceives a lesser number of waves than is actually emitted, and so therefore he perceives a lower frequency. This equation up here, which is similar to what we've seen on the previous slide, but not the same, can be used to compute the frequency perceived by the observer. So in this case, we've got the frequency of the source times the velocity of the wave, which remember is sound, plus or minus the velocity of the observer divided by the velocity of the wave. And plus, use the plus sign where the motion is toward the source, like here, and the minus sign, like here, for where the motion is away from the source. Okay, so here's an example. We've got a train, 150 hertz horn, moving at 35 meters per second in still air, when the speed of sound is 340 meters per second. We want to know the frequency observed by a person standing on the side of the tracks, A as the train approaches, and B as it passes and moves away. So this is an instance from the previous slide where the source is in motion and the observer is at rest. So we have to use that other equation. And so the frequency of the source is 150, velocity of sound is 340 minus 35, so that comes out to be 167 hertz. In this case over here, as the train moves away, everything is the same except this is a plus sign, so that's plus 35, and that comes out to be 136 hertz. So this illustrates what I was talking about in the previous slide. As the train or the car passes the observer, then the frequency, like in this case, is going to shift from 167 hertz down to 136 hertz, which is quite dramatic and easily observable. All right, now just one last thing, and that is that the Doppler effect not only applies to sound waves, it also applies to light waves. And astronomers, when they're analyzing light from stars, observe this thing that's called the redshift. And the redshift means that the light that they observe is shifted towards the red end of the spectrum. Now, the red end of the spectrum is longer wavelength, lower frequency waves. So it's an example of where the source of the light, which in this case is the star, is moving away from the Earth. So this is evidence for an expanding universe. Resonance and standing waves in air columns. All right, so here's a situation where, for example, we would sound a tuning fork over a column of air, and the column of air is in a tube, for example, and the tube here is closed on one end and open at the other. Now, if it vibrates, if the tuning fork vibrates at the natural frequency or the resonant frequency of the air column, then we get a standing wave pattern generated. Now, these are very reminiscent of the standing wave patterns we saw with strings. Only in this case, it's not the string that's vibrating, but it's the air column. Okay, so right here, this would be the fundamental frequency. And notice we use the same terminology. We've got a node here and an antinode here. And the closed end, you're always going to have a node. So one possible configuration is this right here. This is called the fundamental. And you'll notice here that the length of the air column is 1/4 of the wavelength of the wave. So if we put that into the equation, that frequency is equal to the velocity divided by the wavelength, then the wavelength is 4 times the length of that tube. Now here's another kind of possible configuration. Again, we have a node on this end, and we have an antinode on the open end. Only now you can see that this is 3/4 of a wave. So if we plug that into the same equation, frequency is equal to velocity divided by the wavelength, then we end up with the equation velocity is equal to 3v divided by 4l. All right, next possible configuration where we have a node here and an antinode here. Now we can see that the length of the air column is 1 1/4 waves. So the wavelength is 4/5 L. And so plugging that into this equation, we have frequency is equal to 5v divided by 4L. And then here's the next possible configuration right here. And in this case, the frequency is equal to 7v over 4L. Okay, you'll notice that this configuration here is fundamental. This one is the first overtone, which is also called the third harmonic, as you'll see why in a second. This is the second overtone, and it's the fifth harmonic. This is the third overtone, and it's the seventh harmonic. Okay, so looking at the general case here of this equation, the general case is that the frequency is equal to NV divided by 4L. We've got 4L in the denominator in each case, and in one case, the coefficient here for the V is 1, and then 3, and then 5, and then 7. So we're going to call it NV divided by 4L, where N is 1, 3, 5, and 7. And these numbers represent the possible harmonics for a vibrating tube, a vibrating air column in a tube that's closed on one end and open on the other. So here's a problem. We want to calculate the length of a tube closed at one end if it's to vibrate with a fundamental frequency of 128 hertz on a day when the air temperature is 28 degrees. So we're going to use that general formula that we had on the previous slide. And since we want to know the length of the closed tube, we're going to solve for L. First thing we need to do is determine what the speed of sound is. That's determined by the air temperature, which is 28 degrees Celsius. So the velocity of sound is 331 plus 0.6 times 28, or 348 meters per second. Now we can calculate the length of the air column. Notice this is the fundamental frequency. So N here is 1. V is the 348 that we calculated there, divided by 4 over this frequency, which is 128 hertz. So that is 0.679 meters. Now, if the problem asked for the second overtone, for example, then since it's a closed tube, you would have to know that that is the third harmonic. So this frequency 128, that's the fundamental frequency. The first overtone is third harmonic, so that's 128 hertz times 3. Second overtone is the fifth harmonic, so that's 128 times 5, and so on. Okay, now the last case is it's also possible to have a vibrating air column when both ends of the tube are open. And if both ends are open, then we would have to have one of these antinodes on both ends. So this is the first possible configuration where the length of the air column is actually 1/2 of a wavelength. And in this case, the length of the air column is exactly 1 wavelength. And this is, in this case, it's a wavelength and a half. And in this case, it is, what, 2 wavelengths long. Okay, so here is the formulas. So again, we're doing the same thing. We're going to say frequency is equal to V divided by wavelength. We want to put the wavelength in terms of the length of the column. So here it's 2L, and here it's L, and here it's 3V divided by 2L, and in this case it's 2V divided by L. Okay, so again, we want to find a general case here, which is going to be NV divided by 2L. Now, in this case, if we want to have 2L in the denominator in each case, this time the coefficient for V here is just 1. But if we want to have 2 in the denominator, this is going to have to be 2V divided by 2L. This is 3V divided by 2L. And for this one, if we want to have 2L in the denominator, this is going to have to be 4V divided by 2L. So therefore, general case, NV divided by 2L, N is 1, 2, 3, 4. So in this case, the second harmonic is the first overtone, third harmonic is the second overtone, and so on down the line. So for a tube open at both ends, we have harmonics are 1, 2, 3, 4, and remember, if it's closed on one end, then the harmonics are 1, 3, 5, 7.